Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the EE207 Electronic Devices and Circuit course. My name is Deepak Jain. I am an assistant professor at Electrical Engineering Department of IIT Bombay and I will teach this course. So a brief introduction to my research interest. I am interested in semiconductor physics, silicon photonics integrated circuits, fiber optics and fiber based devices, for example lasers, superconducting sources and single photon sources. If you wish to contact me, you can always contact me, and here's my website which you can always visit. If I talk about the course detail, this course will first review the semiconductor physics, then it will focus on the electronic devices like PN junction diodes, transistors, PNP, NPN, BJT transistors, and then it will move to JFET, MOSFETs. So broadly we'll cover the large number of electronic devices, and then we will move to the optoelectronics devices. Basically, those who don't know what is optoelectronics, so before I move to optoelectronics, I will just explain briefly what is photonics. So like electronics, electronics is the technology of controlling the flow of electrons, and photonics is the technology of controlling the flow of photons basically. So in optoelectronics, basically photon can generate the mobile electrons, or electrons can generate the flow of photonics. One of the example is the light emitting diodes. So we will cover some of those aspects like LEDs and some semiconductor lasers. So why this course? The first thing, most important, is the motivation. So as we know that we are all basically using all these semiconductor devices in form of our laptops, computers, mobile phones, if you are using some smart kitchen appliances like microwave oven, maybe a washing machine. So they have basically revolutionized the human life. And if you see the series of Nobel Prize that has been given to the in the area of semiconductor electronics, one of them is the semiconductor amplifiers, which started in 1956, which was given for a point contact semiconductor amplifier, and then in 2000 for the semiconductor heterostructures, which are very important for the photonic devices and integrated circuits. We know how the miniaturization of these electronic devices, the credit goes to the integrated circuits. CCD sensors, basically sensors, you must have used the DSLR cameras, and where these CCD sensors are being used, and also in the medical endoscopes. And the blue light emitting diodes, we all are using these light emitting diodes, which offers much higher efficiency basically than the conventional fluorescent lamp. So a lot of devices has been produced by these semiconductor electronics, and which are in complete use basically. So if I was just talking about the miniaturization, how the semiconductor industry has evolved. If you see basically in 1965, Dr. Gordon E. Moore first presented a paper where he talked about the transistors in a single IC, and he mentioned that it will double every 2 years. So which has basically proved itself. So if I just draw a figure, and where on the x-axis I am having the time, okay, and starting from 1960 to, if I go up to 2010, and if I see the number of transistors, basically if I plot that on y-axis, number of transistors per chip. So starting from a very few number, it has reached to a million level basically. So it has already closed a million level. So let's say this is 1 billion number of transistors on a chip. So you can see how much progress semiconductor industry has made, if you have a look at the processor, microprocessor in your computer or laptop, you will find that the area, surface area of that processor is just few inches square, okay, and the number of transistors in that processor are like hundreds of million basically. So this is what semiconductor industry has achieved in last century. So in this course we will study why semiconductors are so popular, what their physics, what makes them so unique that they are being used so heavily. So to answer this question, what makes them so unique? First is the appropriate energy band gap difference. So for an example, if you are talking about insulators, so let's say this is the conduction band and this is the valence band. So those who don't have any idea about the bands, we'll talk about this band formation in detail in the later part of this lecture, but just assume bands are the basically a band of the energy states, allowed energy states, and these are the valence band where electrons can freely move, and this is the gap, forbidden band basically. So let's say this is Eg, which is the band gap. So in case of insulator, it's much higher than in case of semiconductor. So usually in case of semiconductor, it can go from 0.1 electron volt to approximately, let's say, 3 electron volt. On the contrary, in insulators, it is higher than 3 electron volt. So it is possible to overcome this difference by some thermal energy, by some optical illumination and all that. So this makes this semiconductor more useful than insulator. And in case of conductors, this can be partially filled or both bands can overlap. Okay, so that's the one thing, that this difference between valence band and the conduction band is enough that it can be overcome by thermal energy or some other processes and making them fairly unique. Other thing is that semiconductor materials have negative temperature coefficient. What it means, like we know that in conductors the resistivity increases with increase in the temperature. Okay, resistivity increases with increase in the temperature, but in case of semiconductor materials, resistivity can go down over a range of temperature with increase in the temperature. So in other words, like conductivity goes up. So this is negative temperature coefficient for resistivity basically. So that is also very important. Third thing is the interplay between electrons and holes. So unlike conductors where electrons are only the charge carriers which can constitute the current, but in case of semiconductors there are two particles, electrons and holes, which will constitute the current, and the flow of one controls the another. So this interplay between electrons and holes is very, very important. Fourth thing is it's sensitive to illumination. So photons can create the charge carriers, which also make semiconductors fairly unique and like enhance their functionality and application. Last thing is doping sensitivity. Basically, by inserting other dopants in a semiconductor, one can tweak their properties basically, not just tweak, it can enhance dramatically the properties. So just to give an example of 1 microgram to 1 gram of impurity atoms in a 1 kilogram of semiconductor materials are more than enough to enhance their properties. So doping plays a very critical role in enhancing the properties of the semiconductor materials. Of course, we'll talk about these doping in detail. Now, if I talk about the semiconductor materials basically, just to give you some name. So I'm sure like you are already familiar with germanium, one of the semiconductor materials, and silicon. Silicon is the sort of backbone of the semiconductor industry. Now, but just to inform you that germanium was the first element to be used. Later on, people moved to silicon, and germanium is highly temperature sensitive. That's why it was not a preferred material, highly temperature sensitive. So other semiconductor material is gallium arsenide, which is also being used. Gallium arsenide is a high speed material, And other to mention are like gallium nitride, gallium phosphide. Basically they are useful for light emitting diodes. And so if you just plot the resistivity of these materials, let's say these are semiconductors broadly, and you will find that these are somewhere in between. The resistivity of these semiconductors is in between the conductors. I would like to mention few names of the conductors here. For example, silver and also copper, let's say, aluminum, or whatever spelling you want to use. Also for insulator, let's say some glass, maybe like diamond, pure diamond, and let's say fused quartz. So their resistivity is lower than the resistivity of these semiconductor materials, and this resistivity, resistivity is higher, conductivity is other way around. If I just draw the conductivity on this axis, and resistivity on this axis, or maybe like this way, resistivity. So it's go the other way around, like resistivity is higher in this direction. For conductors it is lowest, semiconductor in between. If I talk about conductivity, for conductors it is highest, for the semiconductors it is in between, and for insulators it is lowest. So these are the few semiconductor materials. We will talk of course about them in detail. Okay, so if I go to group 4, in group 4 we have carbon, silicon, germanium. Okay, if I go to group 5, we have nitrogen, phosphorus, arsenic, antimony. If I go to group 6, I have sulfur, selenium, tellurium, and group 3, boron, aluminum, gallium, indium. For group 2, we have zinc, cadmium. Okay, so if I talk about single element semiconductors, so single element semiconductors, the most famous are silicon and germanium. These are group 4 elements. And if I talk about binary materials, for example 3,5, binary semiconductors, here we have a element from group 3 and one element from group 5. Just to give you an example, aluminum phosphide, group 3 element and group 5 element. Aluminum arsenide, okay, gallium nitride, gallium phosphide, group 3 elements and group 5 element. So these are the binary semiconductors. Other combinations are also possible. For an example, if I talk about binary semiconductors, 2,6. So in this case, we have, for example, zinc sulfide, zinc selenide, and cadmium selenide, cadmium sulfide, and cadmium telluride. Okay, so these are group 2 element, and these are group 6 element. So similarly, you can have binary semiconductors where you have both elements from group 4 only, 4 basically. They are just known as the 4. So example will be silicon carbide and silicon germanium. So these different materials have their own application, different applications due to their different properties. Just to give an example, germanium, as I said, it's a highly temperature sensitive material. So it is not useful for many devices, but because of this high temperature sensitivity, it is useful for many applications as well, for example in photo detection. So similarly, gallium arsenide, which is a fast electronics of fast, like it's offer high speed, so it is useful for high speed electronics. So similarly, just like this zinc sulfide, which is used for TV screen, cadmium selenide used for photo detectors. So depending on the different properties, these different materials have the different application. Okay. And if I just say, just to give an example, like we are talking about gallium arsenide. So why gallium arsenide is faster than silicon? So one thing that comes to mind, that it might be due to the intrinsic charge carriers, free charge carriers. Okay. So let's have a look at the charge carriers of the gallium arsenide and compare it with the case of, let's say, germanium and silicon. So in case of gallium arsenide, the intrinsic charge carriers, basically per cubic centimeter at room temperature, are 1.7 into 10 to the power 6 per centimeter cube. Similarly, for silicon, it is 1.5 into 10 raised to power 10 per centimeter cube. For silicon, yeah. And for germanium, it is 2.5 into 10 raised to power minus 13 per centimeter cube. So if you see, for gallium arsenide, the number of free charge carriers are lowest, 1.7 into 10 raised to power minus 6. But still, it is faster than silicon, faster than germanium. So what it shows that it's not the intrinsic charge carrier which decides the speed. It is something else, and that is known as the electron mobility. So as the name indicates, that this parameter, basically represented by mu n, it shows that how mobiles are the electrons. You may have large number of electrons, but they may not be mobile. You have small number of electrons, but they are more mobile. So in that case, the material will be more faster. And same, this is what is happening in case of the gallium arsenide. Okay. So if I just have a look at the numbers of the electron mobility, for example, in case of germanium, silicon and gallium arsenide, in case of germanium, it is 3900. In case of silicon, it is 1500. In case of gallium arsenide, it is 8500. And unit here is centimeter square per volt second. Okay. So you can see for gallium arsenide, it is much faster. Also for germanium, it is faster than the silicon. So for high speed electronics application, one can use gallium arsenide and germanium over silicon if other things are being satisfied by these two materials. Okay. So now if I just summarize the use of germanium, use of silicon and gallium arsenide, since this course will largely revolve around these three materials, of course, as I discussed about other materials, and I am going to list other materials as well for their different application, but mostly this course will revolve about germanium, silicon, gallium arsenide. So in germanium, as I said, it's a highly temperature sensitive material. So we'll talk about the bands, but just to give you a brief for germanium, this band gap is small here. Let's say this is conduction band and this is valence band. So this makes it a very temperature sensitive. So electrons can easily move from valence band to the conduction band, getting energy from the thermal environment, you can say. So that makes them very temperature sensitive. Second thing is that other than temperature sensitivity, it has higher electron mobility, as we have already seen. So higher, you can say, high speed material. But the fabrication technology is not yet matured for germanium. Okay, so you can say not matured fab or unmatured fab. On the contrary, for silicon, the fabrication technology is absolutely matured, much better, in a much better state than germanium or in gallium arsenide. That's why silicon remains the backbone of the semiconductor industry. Okay, so without any question, semiconductor, the silicon has become the backbone, and low cost, basically, that's another reason you can say. Also, low reverse saturation current. We'll talk about that low reverse saturation current in the next coming lectures. What is that? And ideally, we want this reverse saturation current to be 0, and it has good temperature characteristics, not sensitive like germanium. Okay, good temperature characteristics. Also, it has excellent breakdown voltage levels. So these basically, all these features of silicon makes them very useful for semiconductor industry. So that's why most of the devices use silicon. For gallium arsenide, as we already discussed, it's a high speed one. So also the band gap air is higher, basically, EG, than silicon as well. So it is being also used for optoelectronics application. And it is also being considered as a material for future. As more fabrication technology will develop for this gallium arsenide, material for future. So more number of devices will use this gallium arsenide. Okay, so now we'll talk about more semiconductor materials. So just to give an example, for the binary materials like silicon carbide, we discussed. We talked about aluminum phosphide, we talked about aluminum arsenide, we talked about gallium nitride, we talked about gallium phosphide, gallium arsenide, gallium antimonide. So these are group 3 and group 5, basically. Group 3 and group 5, and initially I was just talking about 4, 4. So these are my, you can say, group 3 to 5 material. And if I talk about 2 to 6 one, I can include zinc oxide. Zinc oxide is a semiconductor. Zinc selenide, zinc sulfide, and zinc selenide, and zinc telluride, cadmium sulfide, cadmium selenide, and cadmium telluride. So these are different kind of materials, and their utility depends on their properties. So they are in the market, or you can say they are in the under investigation. People have been exploring them just because of their different properties. Okay, now so far we talked about the binary semiconductors when it comes to the compounds. Now we'll talk about the ternary semiconductors. Okay, so as the name indicate, it has 3 elements, as you can see here. For example, if I'm talking about group 3 or 5 elements are being used here. So let's say the case of gallium arsenide. So in gallium arsenide, if we replace some atoms of gallium with aluminum, okay, then it becomes aluminum gallium arsenide. This is X, this is 1 minus X. So it shows a fraction of the atoms of aluminum and gallium, basically. So again, the advantage here is the properties, like by adding other dopants you can dramatically enhance the properties, but fabrication is challenge here. Fabrication is fairly difficult. Of course, as you increase the number of atoms of other material, you need to talk about the latest matching and all that. That we'll discuss later on in this course. But fabrication is difficult, but of course the properties are better. So it comes at a price. Okay. So in ternary semiconductors, let's say you have these 2 group 3 elements, and this is one group 5 element. And just to give an example of gallium arsenide, so let's say you are doping some aluminum in gallium arsenide, then you cannot have any random composition. That need to match with the gallium arsenide, lattice matching, the lattice constant. Otherwise, there will be stress in the material. So fortunately, aluminum gallium arsenide have a very nice lattice matching with the gallium arsenide. That's why it's fairly popular. So if I just talk about that, let's say on x-axis I have band gap energy, easy, and on y-axis I have the lattice constant in angstrom. So For gallium arsenide, if you know, the band gap energy is approximately 1.42. Let's say this is 0 and somewhere around you have 1 and this is, let's say, 0.5 and this is just 2. I'm drawing approximately. So this is 1.4 for gallium arsenide and the lattice constant is somewhere around 5.6 approximately. So approximately 5.6 angstroms. Now if you go to the aluminum arsenide, completely aluminum arsenide, so this is somewhere between 2 to 2.5 and what I am talking about here is the band gap energy, aluminum arsenide. And this is slightly above, very slightly above. So you can say somewhere here. So this is, you can say, fairly phase matched. So if you use some atoms of aluminum AX and gallium arsenide, so one would be somewhere in between. So you can peak the band gap basically, okay, while the phase lattice constant is more or less same. Therefore aluminum gallium arsenide is phase matched to the gallium arsenide. There is a compatibility, okay, and this is very important for semiconductor lasers and LEDs. Okay, so now we'll talk about the quaternary semiconductors. As the name indicates, quadrilateral, quaternary. Here you have the 4 elements. So if we are talking about 3, 5, so from group 3 you have 2 elements, and from group 5 you have again 2 elements. So one example would be indium gallium arsenic phosphide. Okay, so here you can say indium gallium are group 3 element, and on the contrary arsenic and phosphorus are group 5 element. So again the fractions will be there, x1 minus x, like x number of gallium atoms have been replaced by indium, and similarly y number of atoms have been replaced by arsenic. So in quaternary semiconductors, which provides an additional degree of freedom than ternary semiconductors, and again the phase this lattice matching has to be there with indium phosphide. So at y is equal to 2.16 1 minus x, you can achieve that, and again it is useful for lasers, detectors and many other applications, but we need to keep in mind this lattice matching has to be there. Okay, so now I will talk about, since we have covered a wide range of semiconductors, the take home message is that depending on the materials, depending on the material property, one can have the different application. So one thing we need to keep in mind, we are limited by the materials. Okay, it's not like that we have n number of materials and we have all the materials which for all the applications we require. We need to come up with new materials, and that's why these binary, ternary and quaternary semiconductors are an attempt in that direction, to come up with new material which can offer some application, some properties which the conventional material is not offering. Okay, so we are limited by the materials. Okay, now I will talk about the crystal structure. So this is the part 2 of this course. So here basically what do you mean by a crystal? You have studied about these in class 12. So if I say I have a crystal, so what happens? Let's say in a crystal you have atoms arranged in a periodic fashion. Something like that. So if I just give an analogy of that, that would be like you have a brick wall, a wall made up of bricks, and so that the bricks are arranged in periodic fashion. I'm having some difficulties here with this active pen, but I hope it should be okay. So a periodic arrangement of the atoms basically. So this is what happens in a crystal structure. On the contrary, in amorphous material, you have something like this, that atoms are there, but there is no periodic arrangement. So unlike crystals, there is no periodic arrangement in case of amorphous materials. Something like that. So this is, you can say, crystalline, crystal nature, crystalline, and this is your amorphous. And the third is polycrystalline, where you have crystal nature but over a, let's say, limited area. And then this is something else, then this is something else. So crystalline nature is there, but different crystals are there. So you can say this is polycrystal or polycrystalline. So in amorphous, there is no periodic structure. Polycrystalline, you can say, composed of many small regions of single crystal material. Okay. And crystalline or crystal is atoms making up the crystal arranged in a periodic fashion. Okay, so you can say there is a basic arrangement which is being repeated over the entire material. So one analogy would be, as I already mentioned, brick. So brick is the basic unit arrangement, and that is being repeated. So this basic unit is known as the unit cell. Okay, and that is the representative of the entire lattice. This unit cell is being repeated to get the entire lattice. So unit cell is the building block, and if you just repeat this unit cell in all the directions, you will get the complete lattice. So this unit cell can be something like, just to give an example, like this. So you have atoms at each corner. Okay, so now let's look into these unit cells in more detail. Basically, what kind of different unit cells we have got. And I'm sure you must have studied about them in class 12. So one of them, first example, is the SCC, which is simple cubic center. Here you have a, let's say, cube. Okay, so you have atoms at each corner of this cube, and this is known as a simple cubic. And similarly, if I talk about the other one, BCC, which is body centered cubic structure. Here you have the similar as of SCC. There is only one addition. Okay, so the only difference is that you have one more atom in the body center. That's why it is BCC, and these are connected to these ones. BCC. Okay, if you ask me like which element, let's say in periodic table, follows these kind of structures, so SCC is being followed only by polonium, and similarly for BCC it's sodium and tungsten, and for SCC it is mainly by polonium. Now if I talk about the third one, which is FCC, which is face centered cubic structure, here it is more or less like this one. The only addition here is the atom on the face, as the name indicates, face centered. Okay, so let's say if we connect this one, sorry for my bad drawing, and we have one atom here, we have one atom here. On each face we have one atom, and they all are connected to the corner atoms. For example, this one is connected to these corner atoms, similarly this is connected to this one, and similarly these ones are connected to this one, and this one is connected to these ones, and these ones are connected to these ones. So that is FCC, and the elements which follow FCC cubic structure are aluminum, gold, and platinum, and also the copper. Okay. So the importance of these unit cell lies in the fact that we can analyze the crystal as a whole by investigating a representative volume. Okay. So you know this unit cell, you can analyze the whole crystal. So it is very important to know what is the basic unit cell for a crystal. And if I talk about semiconductors, which is obvious because we are talking about semiconductor materials, so silicon and germanium. So if I say silicon and germanium, both has a FCC one similar to the diamond structure. So similar to the diamond structure, tetrahedral. Okay, but here it's not just one FCC. So what happens here? You have two FCCs, and both are penetrating in each other. Let's say one FCC is there. So you do have, let's say, one more FCC, same. Okay, but that FCC is inside of this FCC structure, and it is something like, let's say, something like this. So this is basically, you can say one FCC is there, another FCC is there. So it's moved away basically. If there would have been two FCC structure completely overlapping with each other, and one of them has been pushed from the diagonal side with the distance of 1/4. So you can say a unit cell of diamond lattice or the silicon or germanium is being constructed by placing atoms 1/4 from each atom in a FCC at a 1/4 unit distance. The unit distance in a unit cell, the distance between two atoms. Okay, so this is basically the FCC. So two interpenetrating FCC sublattice with one sublattice displaced from another by 1/4 of distance. So this is the structure of the FCC, and similarly for if I say most of these 3,5 compound semiconductors we have talked about, let's say gallium arsenide, they have similar structure, which is known as zinc blende. So zinc blende lattice. Here what we can say is like one FCC sublattice has a column 3 atoms, which is gallium, and the other has the arsenic, group 5 or column 5. Okay. So similarly, if I talk about 2 to 6, it has a slightly different structure, which is known as the wordgite. Okay, so these are some semiconductor lattice structures that we discussed. Now the question comes that the properties of these semiconductors varies along the different directions. They do depend on the crystal orientation, which plane you are in. Okay, so how to refer them basically? That's a good question. So now we will talk about these Miller indices to refer our crystal planes and direction. Just to give an example, for example, let's say this is XYZ something like this. So on x-axis, this plane has some intercept on x-axis. Let's say that is 3a, where a is a unit vector in the x direction, and similarly here it is 2b, and somewhere on the z-axis 2b, let's say 6c. So in order to refer this plane, Miller indices has been defined. And how it has been defined? First you calculate these intercepts on the x, y, z axis, okay, and they should in the integral multiples of the basis vector or unit vector, which I am saying in the form of unit cell. So you can say HKL. So these are the Miller indices represented by HKL. Now the good question comes how to reach to them. Once you know the intercepts, let's say 3, 2, 6 in this case. Okay, first you calculate or you learn these intercepts on x, y, z axis. Then you write down reciprocal of them. So something like 1 by 3, 1 by 2, and 1 by 6. Now you multiply them to bring closer to the nearest integer. So if we want to bring all these three together, so we can multiply it with by 6. So we get somewhere 2, 3, 1. So Miller indices HKL for this plane is 2, 3, K, 2, 3, 1. So once you know the Miller indices 2, 3, 1, you can do the reverse process and you can get the intercepts and you can draw the plane that we are referring. So this way we can refer to a particular crystal plane. Now the question comes, how about the direction? So if I use this notation HKL square bracket in place of this bracket, square bracket, so I am referring to a direction which is perpendicular to this plane 2, 3, K1. Okay, so a direction perpendicular to this, if I say across, so something like that, okay, perpendicular to this plane. So now I hope it is clear like how to refer to the crystal planes and how to refer to the directions. Another thing is like one might say, okay, let's discuss some cases basically. Okay, so for example, you have, let's say this is x-axis, this is y-axis, and let's talk about some of this plane. This plane. So it has some intercept on x-axis. Let's say some number is there, maybe 1, but it don't have any intercept on y and z axis. So how are we going to write the HKL for this case? So for example, mirror indices HKL. In this case, it should be 1 because on the x-axis it has 1, and on the y and z axis there is no intercept. So something like 1 infinite, 1 infinite. So that's why basically if I just talk about A, B, C, and in Miller indices case we need to take a reciprocal of them 1 by 1, 1 by infinity, 1 by infinity, and this comes out to be 1, 0, 0. So HKL here is 1, 0, 0. So that's why this reciprocal is being used here, so that if there is a no intercept, infinite is there, so we can get some finite numbers here. Okay. And another question which can come to your mind is that what will happen if there is a negative intercept? Okay. Let's say in this case you have x, y, z, and on this axis you have some intercept, some plane like this. So in that case we can use negative intercept by h bar. Okay. So these are the ways by which we can refer a particular plane and the directions, and these are very important in the semiconductor. As we will see later in this lecture, that the orientation of the crystal over which you are growing something is very, very important. Now third part of the lecture is the energy bands. This is the last part of the lecture. So as in the beginning I said, we have this valence band and conduction bands. So how this band formation happens? If you have studied a little bit about semiconductors in class 12, you must be knowing that these are the valence band, conduction bands are there, and there is a forbidden band. So forbidden band is the band where you don't have any energy state, any allowed energy state in this valence band and conduction bands. So now we'll talk about why this band formation happens. So in order to understand that, we need to understand that these semiconductor materials cannot be viewed as a collection of non-interacting atoms. As we said, we talked about lattice. So atoms are there at the corner of the lattice. Okay. So now they are interacting with each other. So we can't say, okay, if we have a just single isolated atom, the energy levels that we have studied in class 12, the discrete energy levels, that will not exist. Because these atoms are in close proximity, they will interact with each other. So the valence electrons, the outermost electrons in a particular atom, so once they are in the close proximity of other atoms, they don't just belong to that individual atom, they belong to the whole system. So this close proximity results in these band formation. So if I draw electron energy, let's say, and this is interatomic distance, at some equilibrium distance, let's say A, between two atoms. So what is happening? Initially you had these discrete energy levels. Now when you are bringing these n number of atoms together, what will happen? These energy levels will split, something like this. They will have different energy levels. So still it's finite, you can say, but very closed, placed very close to each other. So these levels. So this, you can say, this is a splitting of this energy level or formation of the bands. So this is applicable for n number of atoms in close proximity. Okay, and this is your electron energy, and this is interatomic distance at some distance, like which is enough to split this. So this leads to the formation of the energy band. So you can say that once this splitting happens, these energy levels of semiconductor take the form of closely spaced. These are closely spaced levels, which takes the form of a continuum. So that's why we call them band. Rather than these discrete energy levels, the same levels. Let's say you have n number of atoms, one level, same level. Okay. But when they are bringing close to together, rather than these n number of atoms, n number of these levels at the same level, they just get at a different level, and it leads to the formation of the energy bands. So this is very important in semiconductors, as I said in the very beginning. So just to give you a more detailed example of that, especially from the silicon case, it has 14 electrons. So let's say nucleus is there, and you have one s2 state, let's say, then you have 2s2 shell. Okay, so you have here 2 electrons, you have here 8 number of electrons in this cell, and then you have these two, third one. So this is 2, 1, n is equal to 1, n is equal to 2, n is equal to 3. So this is your 3s2, and this is your 3p6, where there are 6 states, but only 2 electrons are there. Okay. So as you can see here, this is your nucleus. So innermost levels, the electrons in the innermost levels are fairly close to the nucleus, but the outermost ones are not close, and they interact with other atoms. So same atom is there, which they will interact with each other. So if I draw the band gap diagram for this one, it will be something like this. This is lattice spacing. What is happening here? Let's say I have, for 3s case, I have 2n states if I am talking about n number of atoms. Okay, and it is all filled, as you can see here. 2 electrons are there. On the contrary, there are only 2 electrons. So if I am talking about 2n states, so there are 2n electrons. Similarly here in 3p you have 6n states but only 2n electrons. Okay, so you can say the energy level of these 2n electrons at the same level for n number of atoms. But when you bring them closer, something like this, so they split. Okay, and similarly this splits. And this leads to the formation of these bands. So this is known as, yes, a band, and this is another band, and this is band gap. Because this level is filled and this is empty. So this energy is required from moving from this valence band to the conduction band. Okay, so this splitting is a result of Pauli exclusion principle. In order to obey this Pauli exclusion principle, 2n degenerate state must spread out in the energy. So this is the formation of these energy bands, and this is very important to understand that. So now we'll talk about like some of the movements in the semiconductors. So how the current constitutes and all that. So we know now there is a valence band and there is a conduction band and there is a band gap. So let's say a silicon atom, it is connected to another silicon atom, let's say 4 silicon atoms, as it has tetrahedral structure, we know that. So it is forming 4 bonds, 4 covalent bonds with other 4 silicon atoms. So these are the electrons. So you can see these electrons are in the valence band at the moment. Now let's assume that one of these electrons gets the enough energy and it moves out of this bond from due to thermal energy or something else. So we get a hole here. We get a hole here, and this is our electron. So this electron has moved from here to here. Now what will happen? This electron can move from here to here. Okay, so in this stage what we'll have, it has moved from here to here, so hole is here. So this hole has basically moving from here to here. Similarly, let's say this electron will move from here to here and we will have some hole here. So hole is also moving. If I give you more simplified example, let's say you have few number of these atoms connected, let's say just 1D case. So one electron is moving from here to here and you are getting hole here. Similarly, electron is moving from here to here and hole is automatically shifting in this direction with respect to the electron motion. So electrons are moving in this direction, let's say. So current is being constituted in this direction because of the electron motion. In the other direction, we know charge is negative. For hole, holes are moving in this direction, movement of hole. This is electron movement, but current is also being constituted in this direction because of the hole movement. So this is very important in case of the semiconductors, to consider both the electrons and hole. Of course, we'll talk about them in detail. So we just discussed the formation of these bands, valence band and conduction band. If we just do a fair comparison of insulator that we did in the beginning of this course, insulator, semiconductor, and this is, let's say, just conductors. So what happens? Conduction band, valence band. So in case of insulator, the gap between these valence band and the conduction band. Eg is fairly large, let's say more than 3 electron. In case of semiconductors, this can be fairly small, somewhere 0.1 electron volt to maximum 3 electron. Just to give you some examples, silicon case it is 1.11 electron volt. For germanium it is fairly small, 0.7 electron volt. This makes germanium a temperature sensitive one because the band gap is small, so electrons can easily absorb the energy and move to the conduction band from the valence band. For gallium arsenide it is 1.42 electron volt. Okay. So these band gap also decides a lot of properties. For example, you want to use the semiconductors for light emitting diode application. So what will you do? You will choose the right band, right? Because the energy emitted by the recombination of the electron and holes will depend on this energy band gap, right? So that makes a lot of difference, like for semiconductors, because their band gap are much better, in a much better state. These difference in the energy can be overcome by the different process that we'll talk about in the next lecture. For conductors, just to complete this one, you can say there can be overlap between the both the bands, or they are very, you can say one is filled, another is already filled, partially filled. This is your conduction band, this is your valence band, this is your conduction band, this is your valence band. Conduction band or valence band. Okay. So if I just summarize, we first talked about the semiconductor industry, we talked about the progress in the semiconductors, we talked about the Nobel Prizes in semiconductor electronics, then we talked about the semiconductor materials, elemental, just like silicon, germanium, we talked about binary semiconductors, ternary semiconductors, quaternary semiconductors, then we also talked about the lattice structures, basically unit cells, how the this basically lattice formation happens from the unit cells. We talked about the crystal structure of silicon, germanium, gallium arsenide. We talked about the Miller indices because the property depends on the crystal orientation, direction, plane direction and the plane orientation. So, and then we talked about the energy band formation, how it happens, the valence band, conduction band, band gap. So I think I conclude this lecture here. In the next lecture, we'll talk about the basically energy momentum relations and the doping of the semiconductors. Thank you very much.